Black holes are unimaginably strange. They warp space and twist time, squeeze matter to a vanishing point, and trap light so that it cannot escape. That's why they're called black. Black holes sit in the center of galaxies and shape the universe. But if we can't see them, how do we know they're real? They challenge our notion of space and time. They change our sense of what is real and true. What mysteries they are. What secrets do they hold? Why are black holes so astonishing? I'm Robert Lawrence Kuhn, and Closer to Truth is my journey to find out. I begin at Caltech with the Feynman Professor of Theoretical Physics, Kip Thorne. We meet in Kip's lab, a prototype of a gravity wave detector. Kip is one of the world's leading experts on gravitation, which is the essence of black holes, the dark side of the universe. Kip, describe the structure of black hole.
So a black hole has a horizon, which is the surface of the black hole, except it's not a hard surface like the surface of a billiard ball. And it has a singularity at the center, and it is made in the vicinity of the horizon and down to the singularity by warped space and time. The horizon is a very special place. It's the place that has the property that if you fall into a black hole, you pass through the horizon, you don't notice anything special until you try to get back out, and you can't get back out. You're pulled inexorably toward the center. And we know they are there with 99.9% confidence from observations mixed with a little bit of theory. We know that in our own galaxy there are roughly 100 million of these objects that have sizes of about, say, 10 miles or so across, sizes like that. We know that at the center of our galaxy and almost all other large galaxies, there's a huge black hole that has a size more like the distance between the Earth and the Moon.
And the equivalent of mass of how many suns?
Yes, and in the center of the galaxies, masses of 1 million to 1 billion to 10 billion times the mass of the Sun, all contained in this size that is more like a small piece of our solar system. The smaller black holes, the ones that may be 10 miles across, weighing the same as maybe 10 suns. So they're remarkable objects from that point of view. But the thing that has gripped me about black holes, in the same way as black holes grip by their gravity anything that falls in their vicinity, is the fact that a black hole is an object that is made not from matter, but from warped space and warped time.
What does that mean?
Well, so suppose that you were to measure the circumference around a black hole. And so you go marching around and around, and you see that the circumference is 30 miles. And then suppose that you measure the diameter. You would think that diameter ought to be 30 divided by pi, or 10 miles.
Roughly 10.
But no, you measure that diameter, and it is enormously larger than 10 miles. It may be 1,000 miles, it may be 1 million miles. It's unbelievably large. So space is warped. And you might ask me, well, how is it possible that you can have a huge diameter and a small circumference? Don't the laws of Euclidean geometry forbid it? The answer is yes, they do, so Euclidean geometry doesn't apply. It's like you take a child's trampoline, a large rubber sheet, and you put a heavy rock, very dense rock in the center, and it sinks way down. And then you're an ant, but you're a blind ant, so you can't see what's going on, and you march around and measure the circumference around the trampoline, and then you go in and you measure the diameter by marching down and back up around the rock, and the diameter is huge compared to the circumference.
Wow.
It's the same thing. And that is what the black hole is made of. There is no matter in that black hole. It's not a dense object made of very dense matter. There's no matter at all. There was matter in the star that gave birth to the black hole. Long ago, a star like our sun, but somewhat heavier, will have burned its nuclear fuel, can no longer keep itself puffed out by its internal heat. It starts to cool off, and it then implodes. And all of the matter in that star, much more matter than we have in our sun, goes crashing into the center and is destroyed at what we call a singularity at the center, where that rock was on the child's trampoline. All the matter is destroyed. There's nothing left except this warped space and warped time.
Now, most people would think that if we have this 10-mile object like a big bowling ball, if it was possible not to be destroyed and I got there, I could knock on it, it would be solid. But if I passed through that boundary, I wouldn't know the difference.
That's right, you wouldn't know the difference. However, you would know the difference if you tried to come back out. But there's nothing special at the boundary that you can see locally in your vicinity. There's no hard surface. And if you look above yourself, you can still see the universe above your head. They just can't see you. It's a one-way membrane. Light can come in from the universe into the interior, bringing you an image of what's going on in the universe. But you can't send any light back out to your friends outside to tell you what's going on. You pay the ultimate price when you go in, that you can never publish the results of your explorations. Of course, and by the way, you also die. Einstein taught us that mass and energy are the same thing. You can convert them back and forth, okay?
E equals mc
E
squared.
equals mc squared. And so the mass or energy in this black hole is actually not concentrated in the singularity. It's concentrated in the warping of space and time. In the same way as if you take the child's trampoline and you put the rock on it, and the rock deforms it, it takes energy to deform it. You have to really push on it to deform it. You've got to put energy in to stretch the rubber. In the same way, as the star gives birth to the black hole, the star does a lot of work as it creates the black hole, as it implodes, and all of the mass and energy of the star in the end goes into the warping of space and the warping of time.
Black holes have no matter at all. All their massive gravitation comes from converting the original matter of the exploding star into the equivalent energy, E equals mc squared, and that energy is expressed and trapped in the warping of space and time. The secrets of black holes lie in fundamental law, so that's where I must go. And I go to Leonard Suskind, professor of physics at Stanford and an originator of string theory. What do black holes reveal about fundamental law?
Leonard, the concept of black holes is something that common people can talk about today. To a physicist, and you've studied black holes, why are they so important from a theoretical point of view?
Because they lead to what I would call a conflict of principles. And when principles clash, that's where progress is made. We have two separate theories of nature which are incompatible, apparently, and which need to be put together. One of them is the theory of the very, very small, quantum mechanics. The quantum mechanics of atoms, molecules, and so forth, the uncertainty principle, all these marvelous things that were discovered at the beginning of the 20th century about microscopic physics. At the same time, physicists, Einstein, the same guy incidentally, was also thinking about the very big and the very heavy. He was thinking about gravity. Gravity governs the very big and the very heavy. Quantum mechanics governs the very small. Two different regimes of the world. Then you have black holes. Black holes are objects which belong to both regimes. They're big and they're heavy, but they have quantum properties. In fact, they're very quantum mechanical objects. The fact that they belong to both domains tells us we have no choice. We have to put these two theories together. We have to make sense out of them, even though they appear to conflict with each other. Black holes are the entry into the world that combines them both. So there is a basic paradox and a conflict in the principles of physics that we don't understand at the moment. And that conflict is the laws of quantum mechanics, the laws of information, the laws of physics as we've known them for 300 years, says nothing must ever be lost. And that must say that it cannot pass through the horizon, but must be radiated back out. On the other hand, everything we know about black holes says that things fall into the black hole and are destroyed at the singularity. That is the big conflict that physics is trying to deal with and is trying to reconcile. The answer, whether things fall into black holes and are destroyed, or whether before they actually get to the horizon, they're kicked back out and radiated back out, seems to have the answer that both are true. I will leave you with that. That both are true, but we have to reconcile them. Will that do?
Black holes force us to reconcile quantum mechanics, which describes the smallest features of subatomic particles, with general relativity, which describes the largest features of the entire universe. The two theories, quantum mechanics and general relativity, seem to contradict each other. But that's impossible. So can they be combined? The quest is called quantum gravity. Juan Maldacena at the Institute for Advanced Study in Princeton has remarkable ways to describe quantum gravity and astonishing ways to explain black holes. They're not easy to understand, but really important. I'm going to try.
Black holes are a wonderful thing. They're a wonderful prediction of the Einstein theory of gravity, which is a theory of space-time and how space-time curves and how the geometry of space-time affects the motion of particles and so on. But black holes are also important for understanding quantum gravity, because the whole mass of the star is concentrated in a very tiny region. And when you have lots of matter concentrated on a very small region, quantum effects become important. In the same way that quantum effects are important for an atom, which is a very small thing, quantum effects are important at the singularity. So these quantum effects imply some very strange things, and things that naively contradict the picture of black holes according to the classical theory. So in part, the most surprising thing is that they imply that the black hole will slowly evaporate.
So quantum mechanics says that the black hole can evaporate, whereas classical general relativity says that nothing can escape. It's very compacted, and it's the densest thing you can imagine.
Yeah, that's right. So when you have a space-time that is changing, this background that changes creates fluctuations, creates small perturbations in the fields and in the quantum fields. And so this arises quantum particles that are emitted from the black hole. So these particles could be photons, could be just radiation, could be gravitons, so the quantum of gravity, and neutrinos. And so what this implies is that the black hole is losing energy, it's emitting something. While according to the classical theory, everything should fall into the black hole. So there is some tension between classical and quantum. And if you calculate what this radiation is, you find that this radiation is completely thermal. So thermal means that it's random, it contains no quantum information. However, according to the rules of quantum mechanics, quantum information has to be preserved. So if you knew what fell into the black hole, you should know what comes out of the black hole. So this cannot be completely random in a thermal way. It should only have the randomness of quantum mechanics, which contains some information in it. Otherwise, the rules of quantum mechanics would be wrong and would need to be changed. This is an important question. So do we need to modify the rules of quantum mechanics when we include gravity or not? And some people argued, so Hawking in particular argued that one should modify the rules of quantum mechanics in the presence of black holes. On the other hand, people from, let's say, the string theory community hold this quantum principle as sacred, so in the sense that we're not modifying quantum mechanics. We might modify the nature of space-time, but we don't want to modify quantum mechanics. And one of the main reasons is we don't know how to modify it. So the simplest approach is to, well, let's suppose quantum mechanics is not modified, and let's try to make a theory of space-time and quantum gravity and so on. And so the black hole is a very good laboratory for understanding this problem.
So basically a black hole has been utilized to show the power and the consistency and the triumph of quantum mechanics.
Yeah, that's right. And well, also of string theory, that the fact that string theory originally was made as a theory of small fluctuations of space-time, so small ripples of space-time, but even when you have big deformations like as you have in a black hole, string theory can still describe these things and in a consistent quantum way. So it's a powerful test also on string theory. So it's a very nice achievement of the theory of quantum gravity. Of course, in the future, we'd like to apply similar ideas for describing the Big Bang. But well, we live for the future.
Nothing if not ambitious, describing the Big Bang, quantum gravity, and string theory, all with the same stroke. How far can black holes take us? To find out, to Harvard I go, to meet one of the world's leading young physicists, Nima Arkani-Hamed, whose interests span from quantum theory to cosmology.
From the point of view of well, first of all, black holes were the first place where the full glory of general relativity, in the way that it curves space and time, manifested itself. In fact, the existence of a black hole was so surprising that even Einstein himself didn't really believe that they would physically exist. But black holes are really the first time when a very radical departure from a Newtonian picture of the world was needed. When you add quantum mechanics, black holes are a great little laboratory where the ideas of quantum mechanics and general relativity really collide. While normally we think that the effects of quantum mechanics and gravity should only be important at very, very tiny distances, maybe near the center of the black hole or near the beginning of the universe, since Hawking's realization that black holes actually emit radiation, there's been a very big puzzle known as the black hole information puzzle regarding what happens when you form a black hole and then it evaporates away and gets smaller and smaller until finally it reaches a tiny size and it disappears altogether. This process appears to be describable using only long-distance physics without knowing anything about the details of quantum gravity. On the other hand, when you apply these rules, you get an apparently crazy answer. That information is gobbled up by a black hole. And so if you throw an encyclopedia in, by the time the black hole's gone, all the information in the encyclopedia has totally disappeared. So black holes have a theoretical significance because they're a place where, away from regions where you would think quantum mechanics and gravity are fighting each other, but where the curvatures of space and time are low, everything is very macroscopic, something very funny in quantum is happening in a way that we still don't understand in great detail.
So does that give us any possibility for using black holes as a window into other universes? Are any of these possibilities?
That's a really fascinating possibility. And if we understood the inside of black holes better, we might indeed be able to make such a connection. What we have a good, at least theoretical, understanding of now is what happens when you throw stuff together to make a black hole and it evaporates and the stuff comes out. We still don't understand how to describe what happens to someone who falls into a black hole and eventually hits the singularity of the black hole. And I suspect that progress on that problem will translate to new ways of thinking about the multiverse.
Does the singularity of the black hole have any significance for the singularity of the initial Big Bang?
Well, just as you approach the singularity, energies get higher and higher, curvatures get larger and larger, and it's also a singularity in time because falling towards the center of a black hole has there's nothing you can do to avoid hitting the singularity. Much like in a universe that's collapsing, the march of time makes it impossible to stop you from hitting the inevitable big crunch singularity. That's in fact what characterizes the inside of a black hole. The role of space and time gets reversed relative to what you think is going on outside. And so there's analogies. There's certainly analogies between the black hole singularity and a cosmological singularity. They're not identical in detail, but there's certainly strong analogies between them.
black holes express the full glory of general relativity. But something funny is happening with quantum mechanics. Can black holes give clues to the origin of the universe? To multiple universes? Lee Smolin at the Perimeter Institute for Theoretical Physics challenges current belief. He thinks black holes may generate multiple universes and explain the fitness of ours.
You've hypothesized that black holes can somehow become the mother of future universes. How is that possible?
First, let me say that's not my idea. That's an idea that I learned from my teachers, from Bryce DeWitt, from John Wheeler. It's one of the oldest ideas in the subject of quantum gravity, that when you take quantum mechanics into effect, the singularity at the end of the evolution of the star that collapses to a black hole when everything becomes infinitely dense and time stops, is removed and time continues. Now, where does time continue to? And the most natural point of view is that time continues to a new region of space and time. Since space and time is dynamical and is created by evolution, you create a new region of space and time which can't be perceived from the original region because of the horizon of the black hole. Quantum effects would remove the singularity, so you could keep going, and then you get a new baby universe. What I did was I realized that if the laws changed just a little bit, just like on the average generation to generation in biology in a species, the genes change just a little bit. You don't get a radically different creature when you have a child. Okay? Then there could be natural selection. Then there could be accumulation of positive and negative selection by having more or less progeny. If you imagine now a population of universes growing, there's one each time there's a black hole in our universe. So if the laws change slightly at that event, one gets a large number. It's about 1 billion is what we expect in our universe, black holes. Now let's suppose there's another universe which has a different set of laws that only makes a handful of universes. Then each of those is very close to that, so they're likely also to only make a handful. So after several generations, there's a vast number of ones like ours, and there's a small number of others. Just works just like natural selection in biology. If one therefore imagines after a long time goes by, almost every universe in that population has the property that its parents had a lot of children.
Right.
Because it's much more likely to be the child of a chain of descendants that had lots of children than that had few. Okay. So that leads to an explanation for why are the laws of physics the way they are. And the conclusion is that, again, just like biology, that a typical universe will be very fit. That is, if you change the laws slightly in almost any possible way, you'll get a universe which is either roughly the same or is less fit. That fitness means how many children it produces. Because that's the count of the number.
But why would a universe that selects for black holes be so favorable for life? Why would this possibly be?
Okay, so what then is the singularity, where space and time are destroyed?
Singularity is a mystery. It's a big mystery.
That's why I came to you, to find out the mystery.
Well, I'll tell you about the mystery, I won't tell you the answer.
Black holes reveal the warped side of the universe. Within their horizons, everything we think we know, space and time, particles and forces, changes radically. What emerge are clues about the deep structure of both the largest and the smallest features of our world. On the largest level of galaxies, black holes affect their structure. On the smallest level of quantum mechanics, Black holes are the ultimate proving grounds. Can black holes go further still? Give insight on how the universe began? Generate multiple universes like natural selection in biology? We can never see them, but the light of black holes brings us closer to truth.
For complete interviews and for further information, please visit closertotruth.com.